So we want to talk about the nuclear fusion that's going on inside the sun. This is what's supporting the sun. This is what holds it up against gravity. Now, one of the things we realize is that every second there happens to be 600 million tons worth of hydrogen involved in nuclear fusion. This hydrogen fuses into only 596 million tons of helium. That means every second that the sun is there, 4 million tons of hydrogen is converted into, or 4 million tons of mass, rather, is converted into energy. Remember, E equals mc squared. So E equals mc squared. So that 4 million tons every second is converting into energy. And at that rate, the sun will continue shining for at least 10 billion years. So it can last 10 billion years this way. Now, that's only the core of the sun. Remember, the outer parts of the sun stay hydrogen and helium. It's only the core, the center part where the fusion is happening. There are some indications that there can be a little bit of turbulence and convection in the inner sun, and that might bring some of the hydrogen from the outer layers down in there, and it might actually last possibly 12 billion years, but at least 10 billion years of fusing hydrogen into helium, 4 million tons every second being converted into energy. Now, how this happens is not just, hey, 4 hydrogens run together and make a helium. It's a little more complicated than that. It's actually a lot more complicated than that. The problem is that the hydrogens are protons. The heliums are 2 protons and 2 neutrons. Now, right away, this is where you get this interesting sort of thing that happens, because neutrons are actually heavier than protons, yet we have a helium nucleus, which is 2 protons and 2 neutrons, 2 neutrons being heavier than 2 protons, and yet that helium nucleus is actually lighter than 4 protons or 4 hydrogen nuclei. So this E equals mc squared is where this extra mass is going into energy. The process whereby all this happens in the sun, we call the proton-proton chain, or just the PP chain for short, because it's easier just to say PP than to say proton-proton. And so that's the way that fusion happens in the sun. It's not exactly the same way that fusion happens in a hydrogen bomb, though hydrogen fusion is key there to releasing energy as well. To understand this, we need to know a little bit about the nuclear physics, about what's happening inside of the sun. So it starts off with 2 hydrogen nuclei, and the temperature inside the sun is very high, so they're moving around a lot. The pressure pushes them very close together, and eventually they can be pushed together enough to fuse. Now, what would happen is, as they get close enough together, you have to do work. Now, work in physics, we say, is change in energy. So we increase the energy. So work, the way we figure out work is force times distance. So you push them together a certain distance here, and so what happens is we do work. That's putting energy into the system. Eventually, if you get too much energy, then you end up, again, E equals mc squared. This energy helps convert the one of these protons into a neutron. Well, we put energy into the system, squeezing it together. We convert something, and so now what happens is that it gives off some energy, okay, gives off a neutrino and a positron. Positron is an anti-electron. Now, matter has a associated sort of thing we call antimatter. If you have a particle of matter and a particle of antimatter, and you bring them together, they annihilate each other and give off energy. Energy depending on how much mass is there. E equals mc squared, so the total mass becomes energy. A positron is like an electron, except it's positively charged. If it bumps into a regular electron, which is just normal matter, which is everywhere in the universe, they annihilate each other and they give off 2 gamma rays. The amount of energy in those gamma rays is equal to the mass of the electron and positron put together. So looks like we're doing work putting things together. That's adding energy in there. That energy allows you to make a proton and neutron combination instead of just 2 protons, because a neutron weighs more, so it takes more energy. Now, the interesting thing here is that when you do this, when you put all the stuff together like that, then we have a nucleus here that is a proton and a neutron. Because it's got 1 proton, it's still hydrogen, but it's heavy hydrogen. It is deuterium. This is heavy hydrogen. So the end product, 2 protons came together, we get a deuterium, we spew out a neutrino, and we have these 2 gamma rays. So if you take a deuterium nucleus and you slam it together with a hydrogen, then you get a combination here that is got 2 protons and 1 neutron. Well, it's got 2 protons, so that makes it a helium. But it's only got 3 things in here, so it only weighs 3, and so that makes it a light helium, helium-3. You have to do a lot of work putting this together, so it has a lot of extra energy. That means that energy has to get rid of somehow, and so that energy goes off in the form of a gamma ray. So now we have helium-3, light helium. The helium-3s, if they slam together hard enough, they will actually form a helium-4, because now you've got 2 of these neutrons in there. But you've got 4 protons. You only need 2 protons in here to make a helium, and so you get 2 extra protons spewed out. And so that gives you this helium right here, helium-4, that's your normal everyday helium, and 2 extra protons. They're out there to go back into the fusion process and start making more fusion reactions. So this is a graphic that shows the entire thing. Okay, you got 2 protons coming together. They slam together. They make a deuterium nucleus. The positron spews out, hits an electron, bam, you get annihilation, gets gamma rays coming out, neutrino goes spewing out of the entire thing here, and then eventually another proton comes in here, hits that, makes a helium-3. The entire process is repeated down here. These 2 helium-3s come together, and you get a helium-4 with 2 surplus protons. This is a nice little graphic here that sort of shows the whole thing in which these things come together. And you will see the protons hitting the particles spewing out, get helium-3 right there, another helium-3 made by a similar process, and you get helium-4 with these things left over. So that is what we call the proton-proton chain. And that proton-proton chain is what is the basis of the main source of nuclear fusion inside the sun.